I just want to bring your attention to the idea that I think some people were a little bit flustered after we marked our assignment yesterday. And I think some of these ideas didn't totally sink in, so we're just going to do we're just going to do another example here. So I'm going to pick something, and we're going to, oh yeah, absolutely. Hey, sorry, question 5 is going to be a bonus mark. Does anybody know why I put question 5 as a bonus mark? Because it's what? Yeah, it's a pH range, and it's not, if I'm being perfectly honest, that's not the most crucial thing I would focus on for this unit. But also, I don't know if you noticed, but when I put quiz 6.1 to 6.2, that 6.1 to 6.2 actually is just that first booklet that I handed out. And so somebody called me out on that yesterday, and I said, oh, okay, fine, whatever. So the thing will just mostly be on the pHs. I thought it was appropriate if I asked you what color is the indicator. I thought that's a pretty easy question to ask. So I just want to let you know that hard pH range question, that'll just be a bonus mark. If you didn't get it, then whatever, it doesn't affect your mark. Here, what I want to do is I want to go back to our instructions on writing modified Arrhenius equations. Let's say, you're just going to have to trust me for a second, okay? Let's say that I put sodium oxalate into water. So I put sodium oxalate, and what it does is it turns the solution basic. So how would you indicate to somebody that a solution was basic? What could you say to them that the solution is basic? It doesn't, oh, okay, yeah. So I get what you're saying, right? If something's basic, what does it make, Idris? What does it produce if something's basic? OH. It produces OH, right? That's what you're going with, right? So you're saying sodium oxalate and this solution is basic, right? So it's got a pH of greater than 7, or red litmus turns blue, or something like that. So what we want to say is sodium oxalate, when we put it in water, it's going to produce hydroxide. For sure, no problem. But what we want to know is, okay, let's actually write out our reaction. What am I going to start with? What are the two things in sodium oxalate? Sodium and what else? Oxalate. Can we ignore one of these? First of all, is this an ionic compound? Yes. So can we ignore one of these things? Yes, sodium. You just ignore sodium. Don't worry about it. Because it's, or sorry, not because. Why can we ignore it? It's an ionic compound, and sodium is group 1. It's group 1 ion, and group 1 ions never really do anything. Okay, perfect. So it's the oxalate that we're really worried about. Okay, well let's write down what an oxalate ion looks like. What does an oxalate ion look like to you? Yeah, it's OOCCOO2 minus. And in order for this thing to make hydroxide, what does that have to react with? Water, or H2O. Good. We are 90% of the way there. So we got oxalate because that's the only thing that can react to make a basic solution, right? Sodium can't do it, so oxalate's our only option. When this thing reacts with water, does it pull off a hydrogen or does it add a hydrogen? So this, sorry, it's depending on your perspective, right? Does the oxalate add another hydrogen onto the water, or does it steal a hydrogen away from the water? This steals a hydrogen away from the water, so it makes hydroxide. What are we going to get in addition to hydroxide as our other product? It would be hydrogen oxalate, right? HOOCCO. And is hydrogen oxalate something you've maybe seen before? Yes, absolutely. You can see it on your table of polyatomic ions. I see hydrogen oxalate. Right, oh God, where is it? Right in the middle, there you go, hydrogen oxalate, right there. So let's see, does our equation follow our two rules? Does it follow the law of conservation of mass? Sure looks like it. 4, 5 oxygens, 1 plus 4 is 5 oxygens. 2 hydrogens, 2 hydrogens, 2 carbons, 2 carbons, no problem. Does it follow our other rule? Law of charge. What does the total left side add up to be? 2 minus negative 2, same thing. What does the total right-hand side add up to be? 2 minus. Hey, that's awesome. No problem. That's all we're doing right now. That's all we're doing. We're trying to write an equation that explains why when we put this thing in water, it ends up being basic. Would you have guessed that sodium oxalate would have been basic?
Yeah.
Maybe. What's our traditional definition of something that's basic? It's an ionic hydroxide, right? Is sodium oxalate an ionic hydroxide? No, so most people would probably not guess that this is basic. Does that make sense? We're trying to form some sort of a reason for why this thing makes hydroxide, and this is the explanation of the theory that we're coming up with right now. I don't know, hopefully that kind of makes sense. Hopefully that sheds a little bit more light. What I want to do is, I want to go over these, but I want to go over these a little bit later. I want to give you some time to get into the lab to do some stuff. Do you remember which thing we tested yesterday? Do you remember which substance we tested? It wasn't calcium oxide, it was magnesium oxide, right? And I can't remember. Can you remind me, was this thing acidic or basic? It turned basic, right? We totally saw the red litmus paper turn blue. We had to, wait a couple minutes for it to happen, but yeah, absolutely. So what I want to know, I want to write the equation that explains why does this thing make a basic solution. That's what I want to do right now. So, if I want to explain how this thing makes a basic solution, what's my first step? If it's ionic, we have to ignore what? Group 1, 2, and group 17 ions. Let's take a look at this thing. First question I have for you. How many times have I asked this? Is it ionic? Yes. Does it contain a group 1, 2, or 17 ion? Yes. Magnesium is a group 2 ion. So we're going to ignore it. What would we be left with? If we would be left with oxygen, but there's a very specific name for the ion version of oxygen. Oxide. And what charge does oxide have? It's got a 2 minus charge. So what we're left with is we're left with O2 minus. Now, remember, we're trying to explain how this thing is basic. So, when we put oxide, what is it going to react with in the water? It's going to react with the water. What's our first product going to be? Because we know this solution is basic, what's our first product? Hydroxide. We're doing this one together because this one is an interesting problem. I want you to tell me what we'd be left with. What would you be left with? And what would the charge on the OH be? Oh. Well, that's weird. So when oxide steals a hydrogen away from water, the oxide turns into hydroxide, and then the water turns into hydroxide as well. So yeah, this thing should be basic. Absolutely, it should be basic. Does that make sense? Now, the reason why it wasn't very basic is because magnesium oxide is a low solubility compound. Now, remember back to last unit, if something is a low solubility compound, does that mean absolutely none of it dissolves? No, it means a little bit of it dissolves, right? So what that means is when I put a bunch of magnesium oxide in water, only a tiny amount will actually dissociate. So only a tiny amount will be able to make hydroxide. Does that make sense? That this is, it is, in essence, it is a strong base still because it totally makes hydroxide, but not all of it dissolved. That's a complicated conversation, and don't worry about it, okay? Because we'll talk about it a little bit later on in the unit. What I want you to do is I want you to go out into the lab, and I want you to try to predict the reactions of all of these things. Now, do you know if this thing is acidic or basic?
Yes.
Yeah, you probably should, right? You should know if this is acidic or basic. But then, let's look at the other one. Do you know if this is acidic or basic?
No.
No, you don't. So what you need to do is you need to figure out, is it acidic or basic? You need to go out into the lab and you need to test it using an eyedropper plate. So the way you're going to do it is you're going to grab one of these eyedropper plates, and in the eyedropper plate, there's going to be bins with chemicals out there. You're going to add, like, I don't know, a few drops, fill it up kind of halfway full, right? And how could you test if this thing was acidic or basic? You could, litmus paper, or there's pH paper out there. I prefer litmus paper. pH paper is a little bit wonky sometimes. Sometimes it gives you a neutral substance when it's really not neutral. Okay? It works really well for extremes, but not so much for pHs really close to 7. Okay? So I would prefer that you use pH or litmus paper, but if you want to use pH paper, whatever, it's all good. So you have to test all of these to see if they're acidic or basic, right? On the sheet that I gave you yesterday. Test them, see if your prediction is true, and then if it's basic, what does it make? OH minus. If it's acidic, what does it make? H3O plus. Hydronium, right? How many people are going to screw up their charges? Yeah, everybody's going to screw up at least one charge, okay? And that's totally fine. I want you to try and make the Arrhenius equations for this, and then we're going to try and go over it as a group at the end of class. This is just extra practice for you. I'm not taking this in for marks, but I want you to practice writing these equations. Is that okay? Okay, you need glasses if you don't already wear glasses. We're at the Chem lab.
You're not. You're staying right here. Then why didn't you use the washroom after your test?
But this is what's in charge of it. So that's fine, right? It's just it's already hydroxide, so it doesn't really matter, right? Okay, just give me a second. I want to kind of go through these results because I want to just make sure we're all on the same page for whether or not they were acidic, basic, or neutral. So, acetic acid was acidic, right? Yeah, no, she's just joking, yeah. Ammonia was very strongly basic, right? Calcium hydroxide, same thing, should have been basic. Although, Some people might have gotten a neutral. Okay, I need you to understand that calcium hydroxide is 100% basic. It is basic, totally basic. It's basic, it's basic, basic, basic. Okay, so if you were to test it and leave the red litmus paper in there for like a minute, it would start to turn blue. Wim. It stayed red. It's basic. It's basic. Okay, it's basic. And this is the reason why we're going over this. Okay, it's basic. Okay, magnesium oxide. We already know that's basic. Okay. Hydrochloric acid. Sodium carbonate. Basic. Sodium hydrocarbonate. Okay. Sodium hydrogen sulfate. Do you know what I mean? Did you get those mixed? And then sodium nitrate. So you don't need a reaction for the last one, because you can't explain. It doesn't make hydroxide and it doesn't make hydronium, so there's no reaction that you need to write. Okay?
What about sodium hydroxide?
Oh, sodium hydroxide is basic.
Is that it? Are we all right?
Yeah, it's basic. Sorry, that looks stupid, but hopefully you know what I mean. So that's what I want you to do. I want you to try and explain to me how it is that these things could be acidic or basic. And then I'm gonna go get something. So you can take 10 minutes or whatever, and we'll start working on this. Yeah. Okay. Now the calcium and the hydroxide split up, right? So you don't have OH brackets two. You have hydroxide. Yeah, there's a little bit. And that's a thing that we've seen before.
That's wrong.
I am going to stop you right now, if that's okay. And the reason why I'm stopping you is because I want to make sure we're all on the same page. So, I've seen a bunch of people, and I totally understand, I empathize very greatly why people are doing this. Let's think about sodium carbonate. Is there anything we can ignore in sodium carbonate? Sodium, ignore it, whatever. Okay, so we're just dealing with carbonate. Here's the thing, we have to look at carbonate. If I just said carbonate to you, what would carbonate look like? CO3 2 minus. Right? Yeah, it's okay. So carbonate is really CO3 2 minus. You have to have the charge. You can't just have CO3, because that's not what carbonate is. Carbonate is CO3 2 minus. It's a polyatomic ion. Now, because it's basic, when this thing reacts with water, what does it produce? It produces hydroxide. Now, I really greatly empathize with people when they see, okay, there's that weird rule about non-metal oxides, and what's the rule? You have to react it with 2 waters, right? Okay, calm down, don't change anything on your sheet of paper. Why is this wrong? Totally dead wrong.
But that's
Wim. CO3 2 minus carbonate is a polyatomic ion. It is not a non-metal oxide. When I say non-metal oxide, I mean like a molecule, a totally neutral molecular compound, like PO5 or SO3 or CO2 or something like that. Yeah. Water could technically be one of those, yeah. But when you add water to water, do you get acidic, neutral, or basic? You get neutral, so there's no point writing a reaction, right? But I understand. So you cannot put a 2 there, okay? We can balance this. This is no problem to balance. The CO3, is it giving a hydrogen to the water?
No.
No, it's taking a hydrogen from the water, right? So it's going to turn into HCO3. And if it steals a proton, if it steals a positive, what will the charge now be? 1 negative. And then we see 2 minus over here and 2 minus over here. That works out just fine. What I want to do, totally separately, I want to add carbon dioxide to the water. Now, is this a non-metal oxide? This is a non-metal oxide, carbon dioxide. So this is a non-metal oxide. How do you get a good source of carbon dioxide? Where's a really good, cheap source of carbon dioxide? Not the air. Every single one of you is a good, nice, cheap source. Sorry, I don't mean to call you cheap, but you know what I mean. You're a good, cheap source of carbon dioxide. You can breathe out, and you can make carbon dioxide. Now what I have here is I've got a solution of water and bromothymol blue. Bromothymol blue is blue in basic solutions, green in neutral, and yellow in acidic. And so what we can do is I can breathe through here, and I want to see if it stays blue, then it's basic. If it turns yellow, then it's acidic. So let's try this. Yeah, you can just put them on the counter there. That's fine. Thank you. I don't have to kill you now. Perfect. Sorry. I threatened you. It's fine. Calm down. Are you bothered by the mess?
Yes.
Oh. You see what's happening?
Yes. It's a sit. Oh, wait. Oh, I see.
Is it acidic or basic? It's acidic! It's acidic! It's getting more and more yellow-ish. Okay, so this thing is definitely acidic. So let's write that this thing makes something, right? What am I going to write with? What does carbon dioxide react with?
2H.
It's got to react with, because it's a non-metal oxide, it's got to react with 2 waters. So this is going to be way more complicated than a regular reaction. It's a little bit of math, and that's totally fine. What are you going to make if this solution is acidic? H3O plus. Good. And so all we have to do is we have to keep track of everything that's left over. What is left over from this thing? Okay, 1 hydrogen is left over. Would you agree? H. How many carbons are left over? 1. How many oxygens are left over?
No.
2 plus 2 is 4. And we've used 1 so far, so there's 3 left over. And what charge does the HCO3 have to be? It has to be negative. Why does it have to be negative in this? This charge and that charge have to equal 0, right? Good. So this is us explaining to somebody else how is carbon dioxide acidic? It doesn't have any hydrogen in it. How could it possibly be acidic? It's because, what does it react with? It reacts with water to make hydronium and the polyatomic ion hydrogen carbonate. Does that make sense? Yes. Okay, Wim, question. Almost every single one of them makes a polyatomic ion because that's just the way complicated acid-base reactions go. Acid-base reactions are just often, they include polyatomic ions. And the only way I can explain that away, Wim, is if we were to take chemistry 30 together, buddy. Yep, I know there's been a lot of that, me hand-waving. Take chemistry 30 to learn more about it, but we don't have time to get into it. Okay, so tomorrow, at the very beginning of class, we are going to, man, you got so much time left. Okay, at the very beginning of class, I'm going to put up the key for all of these reactions, and you're going to check. Now, this is not homework. You're not getting marked on it, but it's good for you to understand, okay? We won't have time to explain them, but I'll have time for you to mark them or go through it, and then we're going to move on to something else. Yes, Matt.
I have a question.
You had it last this semester.